In this video, let's learn about definite integrals. Remember from indefinite integrals that a prime of x is equal to f of x. If we take the antiderivative of both sides, well, the antiderivative of the derivative will give us the original function. On the right side, we'll just have the antiderivative of f of x. And we're going to refer to the antiderivative as f with a capital letter of x. So when we see these capital letters, those reflect the antiderivative. If we let f of b be the integral from c to b of f of t dt, and so that represents the area from c to b, and I'll shade this with my little blue lines, and f of a equal the integral from c to a of f of t dt, which would be, well, this little bit right here. Then the integral from c to b of f of t dt, which is f of b, minus the integral from c to a of f of t dt, which is f of a, equal the integral from a to b of f of t dt. That represents the area from a to b, which is the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. That's the fundamental theorem of calculus. All right, so let's first take a look at a couple of just geometric examples. If I were to write this function as y equals 1/2 x plus 3, well, that's just a linear function with a y-intercept of 3 and a slope of 1/2. I'm asked to find the area between -2 and 4. Well, I can go ahead and trace this on my graph and see that that area, it's above the x-axis, and that's what I'm looking for, the area between the curve and the x-axis. So I know my area is going to be positive, and that's just a trapezoid. So if you have a figure that's something from geometry that you can find the area, you are welcome to just use your geometry. If I were to do that, I would add the bases, so 2 plus 5 divided by 2 and multiply by the height, which is 6. So this would give me 7 over 2 times 6 over 1, which would give me 42 over 2, or 21 units. Now, if I were to use calculus, say my curve wasn't so easy, I would find the antiderivative of our function and then evaluate it from the upper to the lower limits. So let's do that. Okay, so this is just 1/2 x plus 3, and I'm looking for the area between -2 and 4, dx. So add 1 to the exponent and divide by that value, plus 3x, and I'm going to evaluate this from 4 to -2. So let's go ahead and clean this up just a little bit right here. Let's see, 1/2 divided by 2, that's 1/2 times 1/2. When you multiply, when you're dividing by a number, you can multiply by the reciprocal. So that's really 1/4 x squared plus 3x, evaluated from 4 to -2. So 1/4 times 4 squared plus 3 times 4 minus, and I'm going to take all of this and subtract the function now evaluated at the lower limit, and that's -2 squared. -2. All right, so 4 squared is 16. A fourth of that is 4, plus 12 gives me 16. All right, let's see. I've got -2 squared is 4. A fourth of that is 1. So this would be -1, and then this would be -6. So 16 minus -5, and that would give me 21 as well. So what I did geometrically, I can do with calculus. Let's take a look at one more just easy geometric example. All right, so this is just the constant y equals -3, which is this line right here. If I wanted to find the area between 1 and 5, that would be super easy. My base times height, well, let's see, my height's a -3, my base is 4. That's just -3 times 4, which would give you -12. Notice my area is below the x-axis, so I know that my area is going to be negative. All right, so now let's use calculus to do the same thing. All right, so this is the antiderivative of the integral from 1 to 5 of -3 dx. The antiderivative would give you -3x evaluated from 1 to 5. And so negative 3 times 5, the upper limit, minus negative 3 times 1, the lower limit. So this would give you negative 15, and plus 3 would give you negative 12. Using calculus, we got the same thing. Let's go through some properties of integrals. Well, this first one is just how to find the antiderivative. You would add 1 to the exponent and divide by that value, plus c, that constant of integration. Okay, so this next property says that if you reverse the boundaries from b to a to b, we can negate that integral. If your boundaries are the same, meaning you're starting and stopping at the same value, you don't have area. That's just equal to 0. If you are multiplying your function by some constant, we can pull that constant out front, then evaluate the integral, and then multiply by that later. This next property says that if we're adding two functions evaluated as some integral from a to b, we can separate those two functions, evaluate them separately, then add or subtract them. In the last property, this is saying if you have some integral from a to b of f of x dx, add some integral from b to c f of x dx, that is equivalent to the integral from a to c of f of x dx. And these last two reminders are, if your function is greater than 0 and a is less than b, you're going to have positive area. That was like that first trapezoid we did. It was above the x-axis, and so our area was positive. The next example that we did, that constant function, was below the x-axis, and so we have the negative area. Let's work through some examples with these properties. So if you're given the integral from 0 to 3 of f of x dx is equal to 6, and the integral from 3 to 7 of f of x dx is equal to negative 8, we're going to determine the values of each of the following integrals using the properties of these definite integrals. And these are on page 71 in your Cycle 2 packet. So let's take a look at this first one. What I notice here is that my boundaries are reversed. Remember up here from 0 to 3 is 6, so if I reverse these boundaries, well, that's just going to just negate it. So that's going to be the negative of 0 to 3 of f of x dx, which is equal to negative 6. In the second example, we're looking at the integral from 0 to 7. Well, I've got 0 to 3 and 3 to 7. I can find it by adding those two integrals together. So this would equal the integral from 0 to 3 of f of x dx plus the integral from 3 to 7 of f of x dx. And this would equal, well, 6 plus a negative 8, or negative 2. All right, in the next example, I'm looking at the area from 3 to 3. Well, if I have the same starting and stopping value, that's not going to have any area. In the next example, let's see, we've got 7 to 3. So I see that my boundaries are reversed, and I've got this coefficient. So I'm going to go ahead and pull that coefficient out and then flip it. So I'm going to have a negative 3 actually from 3 to 7 of f of x dx. And that's going to give you negative 3 times, well, negative 8. And so that's 24. All right, let's try the next one. From 3 to 7, and now I've got two functions in here. So I'm going to separate them out. I'll have to evaluate this 2 by itself, and then I'll pull the 3 out front as well. So let's get started. I'm going to have the integral from 3 to 7 of 2 dx plus 3, the integral from 3 to 7 of f of x dx. Okay, so this first one is actually, let's see, that's going to give me 2x evaluated from 3 to 7. And so let's see, that would give you 14 minus 6, which is 8, plus, and then 3 times from 3 to 7 is negative 8. So 8 plus negative 24, and that would give me negative 16. In number 6, I'm looking for the integral from negative 3 to 3 of f of x dx if f of x is an even function. There is one property, or two actually properties that were left off that chart, and those had to do with even and odd functions. Even functions, of course, are those that reflect over the y-axis, like a parabola. And so your areas would be just mirror images. right? I could just multiply the area of this positive side by 2 to get the area of the whole integral in this case. So I could say, well, 2 times integral from 0 to 3 of f of x dx. And so that would be 2 times 6, which is 12. And in the last problem, we're looking at an odd function. An odd function is one that's going to rotate about the origin. So you'll have some area that's below the x-axis and some area that's above the x-axis. These areas will cancel each other out. So from negative 3 to 3, if the function is odd, is going to equal 0. Okay, so back to a geometric problem. Let's go ahead and work through some more examples. The graph of the function consists of a semicircle and 2 line segments as shown on the graph. Let g of x equal the integral from 1 to x of f of t dt. Find g of 1. So g of 1 is equal to the integral from 1 to 1 of f of t dt. Right away, you should see that the boundaries are the same, and so that's 0. G of 3 would equal from 1 to 3 of f of t dt. And let's see, from 1 to 3, that would be the area below the x-axis, this little triangle right here. And so that would be, well, base times height divided by 2. And so that would just be negative 1. And in the last one, g of negative 1, let's see. So that would be g of negative 1. It's the integral from 1 to negative 1 of f of t dt. I'm going to go ahead and reverse the boundaries. So that's going to be negative 1 to 1 of f of t dt. Notice I put the negative out front. And so now I just need to find the area from negative 1 to 1. Okay, so let's see. Negative 1 is right here to 1 would be this quarter of a circle right here. And so I just need to find the area of that. And that would be, let's see, pi times the radius squared divided by 4. And it is going to be negative because I had to reverse the boundaries. So let's see, how about just negative pi? Let's take a look at some of these problems and see if we can work these out. I need the antiderivative of sine x. Well, the derivative of cosine is negative sine. So if I wanted positive sine, I'm going to have a negative cosine of x evaluated from pi over 4 to pi. And so this would give me negative cosine of pi minus negative cosine of pi over 4. So let's see, the x value at pi is negative 1. A double negative makes that positive 1. The x value at pi over 4 is root 2 over 2, so that would be plus root 2 over 2. In the next one, if I have 3 over x, I would recognize that that is the natural log function, and so this would be ln, or 3 ln of x, and that's evaluated from e to 1. And so this would be, well, 3 ln of e minus 3 ln of 1. L and e are inverses, so this is just 3, and e to what exponent gives you 1? That would be 0. And so your final answer is just 3 here. Don't forget about your inverse sine, inverse tangent. What we've got here is the integral from half to square root 3 over 2 of 1 over root 1 minus x squared, and I recognize that as the inverse sine. And so this would be inverse sine of x evaluated from 1/2 to root 3 over 2. We're going to go ahead and just stay with quadrant 1 unless it's stated otherwise. So we're looking for what angle has a sine value of root 3 over 2 minus what angle has a sine value of 1/2. Well, in first quadrant, a y value of root 3 over 2 is going to happen at pi over 3, and a y value of 1/2 is going to be at pi over 6. So this is pi over 3 minus pi over 6, and you can leave it just like that. In the last example, let's see, I'm going to go ahead and rewrite this as the integral from 1 over 9 to 2x to the negative half dx. Let's go ahead and add 1 to the exponent, so that gives you 2x to the positive 1/2, and we divide by 1/2, And so I'm going to go ahead and flip and multiply, and then I'll evaluate it. So that would give you 4x to the 1/2 evaluated from 1 to 9. If I plug in 9, 9 to the half is 3 times 4 is 12. And if I plug in 1, 1 to the half is 1 times 4 is 4. So that's 12 minus 4, and that's 8. Okay, a couple more examples. A little bit more complicated, I don't know. Polynomial, those are pretty easy actually. So let's find the integral. So that would be 2x cubed over 3 plus 4x squared over 2 minus 1x evaluated from 2 to negative 1. Oh, and this one is on page 72 in your packet. So this would give you 2 times 2 cubed over 3 plus 4 times 2 squared over 2 minus 1 times 2 minus, and this would be, well, 2 times 1 cubed over 3, 4 times 1 squared over 2 minus 1 times 1. All right, so 2 cubed is 8 times 2 is 16/3. 2 squared is 4 times 4 is 16 divided by 2 is 8 minus 2. And let's see, minus 1 cubed is 1 times 2 is 2, so that's minus 2/3. And then 1 squared is 1 times 4 is 4 divided by 2 is 2, so that'd be minus 2. I'm just going to go ahead and distribute the 2, and I can go ahead and get rid of these actually. If I'm distributing at the same time, I don't need parentheses or anything. And then this would be negative 1, so plus 1. Let's go ahead and clean this up. 16, and this is a double negative, so that's plus. So that's 18/3, which works out nicely. 8 minus 2 is 6. Minus 2 is 4, plus 1 is 5. And so that would be 6 plus 5, and I get 11. All right, and this last one, I recognize that this will give me the natural log. And so this is ln x evaluated from e cubed to 1. And so that's ln e cubed minus ln of 1. And so this is 3 minus 0, which is just 3. Another graph. This one consists of line segments and a semicircle. Evaluate each integral using geometric formulas. Okay, so I'm just using geometry here. From 0 to 2 would be this quarter circle right here. It's below the x-axis, so I know that's going to be a negative. And then pi r squared divided by 4, and so that's just negative pi. From 2 to 6, well, that gives me the area of this triangle here, and that would give me just, well, 1/2 base times height, and that would just give me 4. And then the integral from negative 4 to 2. Okay, so let's see, negative 4 would be all of this, all of this, all of this. So a semicircle below the x-axis and a triangle below the x-axis. So let's see, base times height of the triangle would be 2 times 1 divided by 2, so that would be a negative 1 since it's below the x-axis. And then the semicircle, which would be pi times radius squared divided by 2, so that would give you 2 pi. And so this would be negative 1 plus 2 pi. Okay, let's take a look. We've got some more problems. From negative 4 to 6 now. Okay, so on the previous example, let's see, we had negative 4 to 2 and 2 to 6. So we're going from negative 4 to 6. So what I can do is I can just add the 4 and the negative 1 plus 2 pi. So this is going to be the integral from negative 4 to 2, and then of f of x dx, plus the integral from 2 to 6 of f of x dx. And so that's going to give me, well, negative 4 to 2 was negative 1 plus 2 pi. And then from 2 to 6 was 4. And so this gives you, well, 3 plus 2 pi. All right, so the absolute value of the integral from negative 4 to 6, well, come back up here. Let's find the absolute value of these. And so the absolute value of this first integral would give you 1 plus 2 pi plus 4. So that would be 2 pi plus 5. And then this last one, okay, so in this problem, I've got two functions. So I'm going to separate them. So this is the integral from -4 to 6. And I already know that that is 2 pi plus 5. So let's see. I don't need that bracket. Let me get rid of that real quick. Plus the integral from -4 to 6 of 2 dx. Okay, the tricky part is this part because I have to find the antiderivative and evaluate that. I already know this first part. So let's work on this second part. So this would give me 2x evaluated from -4 to 6. So that's going to be 12 minus, and if I plugged in a -4, that would be -8. So 12 plus 8, and so that's 20. And then if I already know the integral from -4 to 6 is 3 plus 2 pi. So 3 plus 2 pi plus 20 would give you 23 plus 2 pi. And I think that's it.